We started with chapter 14 after the last test. We went to chapter 15, and then we took a look at the beginning of 17 today, or yesterday. I haven't honestly made the test yet. I still have to do that tonight. I always have my old tests from the years before, so I know what I'm going to generally put on it, but I always change them, so I have to still make the actual test. So I'm guessing lengthwise it'll be about the same as always, if anything a little bit shorter, because tomorrow's a B with examine. Okay? So just period-wise, length is period. Yeah, I don't know. I don't know how many it's going to be. I'm going to guess it'll be like 50 or 60 points. Probably the same as usual. We'll see. So, chapter 14. What was chapter 14 about? What was the idea behind 14? What was it? Yes. What's the topic, though? Yeah. So, yeah, we did a lot with light and EM spectrum. Good. So let's start with 14. Let's start with the ideas first, where we looked at the EM spectrum in the beginning of chapter 14. We talked about the different types of waves that can occur. We talked about radio waves. We talked about gamma rays. We talked about all different types.
This is a question, but are we going to have to know, for all the different types of waves, do we have to know the frequency of and wavelength, or just the
general trends? So I'll go over that now. So in that table, if you recall, you were given wavelength, frequency for every type of wave, or range, and you were given some applications. The applications are really the important part that I'm going to have you on. The wavelength and the frequency, that part you should know that following is true. As the wavelength, so if you remember the table was drawn with the highest wavelength at the top. That was radio waves. And the smallest wavelength at the bottom of the table, that was gamma. All right? That was the general format, and everything in between was in there. And then, as a result, if the highest wavelength was at the top, it was the lowest frequency. And at the bottom, this was the highest frequency. So you should remember the fact that frequency and wavelength are inversely related. If something has a higher frequency, it has a lower wavelength. Now, you should also know that generally speaking, the wavelengths are shorter at the bottom. And if we look at that, we can think back to the idea where we discussed how gamma rays and X-rays and different types of rays at this end of the spectrum can harm people, can mutate you, or can cause you to get some sort of change in your cell structure in your body. The reason, again, is because the wavelengths are so small. The wavelengths down here are on the scale of nanometers. So when you go get X-ray, how does it work again? The wavelengths themselves are smaller than the actual cells when you're going through your body. So the X-ray is able to penetrate your skin and then show up on that, what's that called? Like a film. The film that's behind you showing the image. Because of the fact that you have small wavelengths. How many people listen to the radio? Honestly, you listen to the radio, do you get harmed by it? Does it hurt your body? No. Because radio waves, the wavelength of radio waves are like 30 centimeters, 70 centimeters. So we're looking at much larger values for wavelength of radio waves, so they're not able to harm you. Then we talked about a lot of applications. You should definitely know the applications. Doesn't mean you have to know every single one, but be able to give an example of that, give you a random, pick a random type of wave that we talked about. Gamma, all right. What's an application of gamma rays? What was one of the applications? Types of what? Cancer treatment was one of them, yeah. Gamma rays. What else? Sterilization was, I think, both gamma and UV or something. What? Ultraviolet was also, for sterilization. So being able to come up with one of the applications or provide one, or maybe being able to choose one of 4 choices, that might be an application for that type of wave. Or maybe I'll say, which of the following wave types might be used for heat vision? Which wave was that? Infrared, very good. So understanding which is which, but not necessarily being able to spit all of them out. Okay, so maybe study the applications along the right side of the table, and understand that the wavelength is higher at the top, lower at the bottom, to explain that idea, and then the fact that these are inversely related. Max is here, min is here. When min is here, max is here. Okay? That was the beginning of 14, though. That was only the very beginning. We also talked about how EM waves all travel at the same speed. What was that speed called? C. Very good. Okay, and C is defined as the speed of light. All right? So let's discuss that for a minute now. So we've got this value C, which is 3 times 10 to the 8 meters per second. Okay, 3 times 10 to the 8. So, what do we know about the speed of light? Give me something about it we know.
It's the fastest anything can travel.
It's the finite absolute maximum, absolutely, of anything that can travel. What else?
Like in a vacuum.
That's in a vacuum, very good. So this maximum speed can only be attained in a vacuum. Even in air, it does slow down a little, which is why the index of refraction for air is really not 1. It's like 1.000297 or something other decimals. So it does slow down when it enters other media. Okay, so the speed of light is assumed to be in a vacuum, this number. But the minute light is now traveling under water, or through glass, or through some other translucent medium, it's going to change its speed. That change in speed, if you recall, we'll get to this in a minute, but is what causes refraction, the bending of light. Okay, so we know that this idea is true. Let's see. What else from 14.1 I'm trying to think back to? Is there anything in your notes that you were confused about from 14.1 if you look at it? No? Oh, Victoria, you have a hand or no?
Well, this,
Yeah.
I don't know if it's for the section, but when it's like, well, it's like hertz and stuff, but it was like
Okay.
hertz.
Megahertz?
Yeah, megahertz. So then, like, how do you convert that? Or you can't.
So mega is times 10 to the 6.
Okay.
So if you were told that it's 89 megahertz, you would write 89 times 10 to the 6 hertz.
Okay.
Like kilo is 10 to the 3, just 6. Yes?
We just gently went over brightness of light. Is that
We did. We quickly talked about brightness of light. That was that in 14.1? Yeah, and you have to understand the relationship conceptually that exists. So as you get further from the light source, the brightness, fades or decreases. Very good. And how does it decrease by? By a function of what? Like if I double the distance, the brightness goes down by a factor of, you have to square it. So 4, yeah. So if I triple the distance from the light source, the brightness goes down by a factor of 9. It's always squared, okay, the relationship there. Brightness is always squared as far as the distance is concerned away.
Going back to what Victoria said, for one problem on the problem set, it's probably really simple and I didn't get it. It's like n hertz. Is that like nano?
Lowercase n?
Yeah.
Nanohertz. Nanohertz.
What is that? 10 to
Times 10 to the negative 9.
Okay.
Okay,
Should we
nano
know
says.
that as well?
I mean, at this point in the year,
10 to
you
the
should
negative
know
Or
10 to
just,
the negative 9.
right.
You should know kilo for short. You should know mega for short. You should know centi, milli. We've done enough with those. We haven't done much with micro or nano, so I don't plan on giving you a question with those prefixes because we haven't really done a lot. But centi, milli, kilo, mega, those ones you should definitely know what it is. Yeah.
We're like G.
G, gigahertz, 10 to the 9. You have to know it. I'm not going to give you a question that involves gigahertz. I can tell you that, but it's something that's good to know. And if you recall, just think about like computers. There's 1,000 megabytes in a gigabyte, approximately. It's not exact. So if one is 10 to the 6, the next one becomes 10 to the 9, because 1,000 is a factor of 3 of increase, 10 to the 3rd. So if you know that mega is 10 to the 6, giga is just 3 more than that, because there's 1,000 megabytes in a gigabyte. Anything else from 14.1? All right, 14.2, 14.4, we looked at a lot in that section, right? We did a good amount of stuff in those 2 pages of notes. So what we started with in this section, or what we did, some of the things that we did in there, was we talked about how light travels, how it's affected with polarization, with color, with dispersion. What else did we do in 14.2, 14.4? What do you have in the beginning of your notes for 14.2 and 14.4? Diffuse versus specular surfaces, good. What was the difference there? What's diffuse and what's specular? What do those mean?
It's the A parallel cuts off parallel.
Okay, so for example,
Like, if you have, like, lotion, the light's gonna be diffused, but if you have like a piece of glass, it's gonna be spread.
okay, you're on the right track. The surface is diffuse or specular, but the light comes off, like you said, parallel. So for a specular surface, think of like a mirror. The mirror reflects your image perfectly off of it. For a diffuse surface, think of like, I don't know, this wood trim I said the other class. This would be diffuse. You're not getting a reflection off of this from the light. These tables, though, are actually pretty specular. The way you can tell is as I move away, I can see the shininess change. I can see that it reflects light differently depending on the angle on that. So clearly this must be somewhat specular. Now, a true, like, perfectly specular surface is not really possible, right? Because everything, even at like the microscopic level, is going to have some ridges or some impurities. So you can't be like really, what's the word? You can't be a stickler about this. If something seems smooth, we call it specular. If something is clearly not smooth and it's not reflecting anything, we call it diffuse. Okay? Yeah.
Basically, we can't see any sort of reflection in an object.
We're looking at diffuse there, yeah, exactly. Okay? Those are the two different types of surfaces that we had looked at. Let's see. So we also talked about, in that section, the idea of polarization and what polarization is. And this led us to several things, but one of the things that we talked about with polarization was some applications of it. What were some applications of polarization? Polarization, yeah.
Sunglasses to keep the sun.
Yeah. So we looked at sunglasses to keep like the glare and certain rays to change the orientation. Anybody remember how polarization works? What it's doing?
It aligns the rays of light like all in the same way because like when rays of light go through something like glass, the light wave can go one way and the magnetic wave can go another way, and then they can change for all the different rays, but when it goes through something polarized, they're all the same way.
Yeah, so it's exactly right. You're reorienting the EM waves. So you have your magnetic and you have your electric. Okay, those two different waves, they're always perpendicular to each other. The question is, this one might be traveling like this, whereas this one might be traveling like this. Well, that's unpolarized light. Polarized light realigns it so that the transmission axis is always perpendicular, and as a result, the waves themselves move in tandem, or they look literally like the same waves just shifted next to one another. So we talked about glasses. We also talked about like cars, the front windows of cars. Ones that are polarized don't give off glare, so it helps reduce glare. Computer screens. The light that comes out of your computer screen is unpolarized. There's a layer of polarizing film on your computer screen on the actual LCD that enables you to see what's coming out of it. If that polarized film was not there, you would literally see a blank white screen. You wouldn't see anything. Okay, so it has to reorient the EM waves in order for you to see it properly. So understand the general idea, and then be able to explain maybe an application or two, or pick an application or two out of several choices if they're provided. Let's see. We talked about dispersion. What was dispersion? We talked about that real quickly at the end of the class. What was dispersion? Or what's an example of dispersion? Yeah, Kira.
Isn't it presence of light or like?
Dispersion of light, yep.
Isn't it everything a prism and then it goes off the other?
Exactly. Dispersion is really a way of refracting light, but specifically refracting white light, so that it provides all the different colors of the spectrum. So a good example is a prism or raindrops, or anything that breaks up white light into its components. Why might that be important? Why might that be important? Right? What application could it be? We never discussed any applications, but I'm just curious, why would you want to break up the color of white light into its different colors of the spectrum?
See if the stone is moving.
Okay, testing for something whether it's truly a certain material or not. That's good. Material properties. Because only certain materials are going to break up the light into certain things. That's good. That's like a forensics idea. You want to see if material is a specific type. Anything else? Alright, I'm just curious, I was just thinking off the top of my head.
We have to name any application.
No, I was just trying to think about like what are some reasonings that you could think of this as, related to real life, but we never went into detail on that in class.
Mr. Allen?
Yeah.
On the problem sets, there's a question about prism, and like how they capture light with the critical angle. Is the critical angle in a prism always the top corner, or the angle of what gives you?
Well, it depends on which way the light is entering, but it's always the angle that, like, so for example, a prism is triangular, right? You're talking about triangular prism, right? Okay, because you can have rectangular. So a prism has a triangle base and then it's extruded upward. So you have a triangle with another triangle, they meet. The angle that they come to in the triangle, that's the angle you have to look at to compare to the critical angle. So for example, if the prism from bird's eye view, okay, here's the prism you're looking from above, light goes through the prism, let's say perpendicular to the surface, so it doesn't bend. Remember, if you're ever going right perpendicular to the surface, the light isn't going to bend. But when it's attempting to leave, thing is, if this angle that it hits at is large enough, see this angle? Here's the normal. There's the normal right there. That's the angle theta, right? If that angle is great enough or greater than the critical angle, the light will be trapped inside of the prism. Similar to the way a diamond traps light. Okay, so if this angle exceeds the critical angle of that material property, this light will not pass through any event. What will happen is it will bend back in. Okay? But it's the same, it's the same thing as a diamond or some sort of a stone that traps light. It sparkles. Let's see. Anything else? Oh, we talked about how color really works. What's the idea of color and light? Not pigments, but light color. How does light color work? So for example, the color that you're seeing, not like paint colors that you're like mixing paint together. Okay.
Aren't they just like different frequencies of light?
So if you're seeing red, you're seeing one frequency. If you're seeing green, you're seeing another frequency. Now, when you see a color specifically, like when I see blue, I'm seeing that frequency, but what else is happening behind the scenes?
It's reflecting.
It's reflecting.
Instead of being absorbed.
Yeah, it's reflecting that color. So when you see blue, every other frequency is being absorbed by the material except for blue. Whatever frequency length whatever frequency length that's on, okay, that's what's being reflected back towards you, the blue. We talked about black being the absorption of all colors, white being the reflection of all colors, which is why if you think about how a prism breaks up light to all the colors, when you see in white, you're literally seeing every color at the same time. That's what white light really is. What else? Anything else in 14.2, 14.4 you have a question on? Alright. Let's go to chapter 15 where we spent a lot of time really on. Okay, chapter 15 was all about refraction. We started chapter 15 with the simplest law ever. It was called the law of reflection. What did the law of reflection tell us? Simplest law. Pat?
That, like the angle the light comes in, it goes out in the same angle.
Exactly. So if I draw my normal in here, there's my normal. My normal is always perpendicular to the surface. If this angle is theta 1, and the light ray comes in like this, and it hits a specular surface, the way it will reflect will be at the exact same angle, theta 2. Okay, that's really what the law of reflection is telling us. That those two angles are equivalent to one another. Yeah.
You're talking about if light enters, or?
If anything gets reflected off of any EM wave gets reflected off of a specular surface, the angle it comes in at will equal the angle it exits.
Okay.
Not the same for refraction though, right? Refraction is where it's bending, so the angle is actually changing there.
Yeah. There was a problem on the problem sets that said there were two mirrors and a beam of light came in at
35-degree angle.
Yeah, and then it bounced off of the other angle, and you had to find the angle it came out on.
Mm-hmm.
Yeah, that was like.
You want to go over it real quick?
Yeah.
So, what you would do for this one, so Paul is making a good point, because a lot of you asked me this question the other day. Here we have this double mirror setup, and we know that this light ray is coming in at an angle of 35 degrees to the normal. I mean, it's not my stylus, guys. I'm doing my best. I lost one. All right, so there's the normal, this dashed line right here. So it came in at a 35-degree angle. It then got bounced back out at some unknown angle. It was called theta 2. We didn't really know, although we know it's going to be 35. It hit here, and then this one bounced off here. And the question really in this problem was to figure out the angle that it exits this one with. Figure out that theta right there. So it's all geometry here. So if the incoming angle is 35, the first mirror is going to reflect it with 35 right here. If that's 35, then this is definitely 55, because together 35 and 55 make 90. And I can clearly see that this is a right angle. The normal is always drawn perpendicular, so this has to be 90. Well, if that's 55 and this is 90, well then this is 35 again. Because the sum of three angles of any right triangle or any triangle is 180. 55, 35, and 90 is 180. Well, if that's 35, then we go back to 55. So this must be 55. Well, if that's 55, then theta itself is also 55. So it turned out that the answer in this one was 55. If I think the incoming was 35, right? Yeah. And it said, what do you notice about this? You recognize that they are complementary. And that will always be true. If the angle of the mirrors is 90, though, clearly, right? This angle has to be 90 for this to be true.
Do we need to know how to do that?
I mean, you should know the law of reflection and how to apply it to any given scenario. Maybe not that exact example, but understanding how light bounces off one surface and then maybe hits another surface, you should be able to understand that. The geometry at least involved. Okay, again, it's all right triangles. Look at this. This is a right triangle right here. That's a right triangle, so that's 90 right there. Another right triangle. That's 90 right there. So it's a bunch of right triangles. That's all it is. What else? Let's continue in 15.1. We then talked about refraction right after reflection in 15.1. And what was refraction defined as? What's refraction really? Yeah, right? The bending or the curving or the reorienting of light. Now, why is that happening is the real question. Victoria?
Oh, did you want us to answer that, or were you going to answer it?
You.
Are you
Yep.
sure?
Yeah,
No,
I just didn't look up.
okay. No, but I thought he was going to answer it, and then I raised my hand. Was it because it's like switching, like if it's going from like air to water, or like going through glass or something, or like it depends on the surface, something like that?
Something to do with the materials for sure.
Curious,
It has to do with materials. Give me more.
And so when it goes through the materials, different materials, they have a index of refraction, and that basically tells you if it can bend towards the normal or away from the normal.
Good.
And doesn't it also have to do something with, like, I guess it's changing the speed?
Yeah, that's the other part.
Yeah.
The conceptual understanding is the speed. Mathematically, it's the indices of refraction you can use to calculate. So what's physically happening, light travels fastest in air, like we said, or vacuum. But when it hits other media, it slows down. So when it slows down is when you're seeing the light bend. Okay? And remember, so for example here, let's draw this example in here. So let's draw a light ray coming in like this. Okay, from air to water. Now, if it's slowing down, who remembers, does it move away or bend toward the normal? Bends toward the normal. So, if I called this theta, hypothetically speaking, 28 degrees, what do you know about the refracted angle? What must it be? Not numerically, but something less than 28. Okay, clearly because it's bending toward the normal means it becomes smaller of an angle. Bending away from the normal would be like out here. Okay? So all we're saying is that the angle of refraction gets smaller. This angle here, theta r, must be less than 28. We don't know what it is until we use Snell's law and we use our indices of refraction. But we do know that it's got to be less than 28 because it's slowing down. So if you're forgetting this, right, you want to remember, slowing down, when you think of slowing down, you think of lower velocity, don't you? Yeah. And isn't the angle getting smaller? Isn't the number getting smaller? So think about you're reducing the velocity, you're also reducing the angle. Okay, that's how you can think of the correlation. This angle gets smaller the angle of 28 becomes something like 10. It gets smaller. Well, it's because the velocity is getting smaller. So if you want to remember that, that might help you to think of it that way. A lot of students have been forgetting which way it works and stuff. So try to come up with mnemonic devices for yourself. Let's see what else. All right, now, whenever it goes from slower moving media to faster moving media, the opposite happens, right? We're understanding that? So if it goes from faster to slower, it bends toward the normal. So if it went from slower to faster, it would bend away from the normal. That's what allows total internal reflection to occur. So let's talk about that theoretically now. We'll get to math in a minute. But let's talk about that. Look at another surface interface. Now, the water's here still, and air is still here, but now the ray is being projected from the water outward. So, let's pick an angle. Let's say this is 50 degrees. I'm picking arbitrary numbers right now, okay? So if that angle is 50 degrees and it goes from water to air, we know it's going to bend away from the normal. So the next angle is something bigger than 50. Give me a number bigger than 50, but not more than 90. 75. So we have an angle here now of 75 degrees. So 75 degrees, this would be 45, maybe 60, 75. So there's my light right now. So we can see that clearly this, if it were continuing, right, if this ray had continued, it would have followed this trajectory, right? It would have gone like this. Instead of following the path that I'm currently highlighting, it bent away from the normal. That's what we mean by away from the normal there. Now, what happens when I increase the angle of incidence? See this 50 at the bottom? If I increase 50, what's going to happen on the other end? Jake?
It'll increase your angle bending away from the normal.
Exactly. So if I made this say 60, 75 might become 80. 80, okay. Now, eventually it's going to become 90 degrees, right? Instead of 75. If I keep increasing this angle of incidence, that other angle is going to get bigger and bigger until it becomes 90. When that angle becomes 90, this angle is now called critical. That's the whole idea behind critical angles. So watch, I'll draw you a little quick diagram here. Yeah.
Your critical angle is the resulting angle?
Is the incident angle, the first angle.
Okay.
Okay? One sec. Not right now. Wait till you're done. Not right now. You need to review this. I increase this angle. I make this angle, say, 65 degrees. Okay? So now, as a result, this other angle gets much bigger. The refracted angle now might be 85 degrees. Okay? But eventually, what's going to happen is, this angle might get to a number that causes this to be 90 degrees. When that happens, this angle is now called a critical angle. So let's say hypothetically that when this incident angle becomes 70, so we take this laser, right? So there's like a little laser pointer here. So here's your laser pointer right here. You're moving the laser pointer. You take the laser pointer, move it a little bit further until you're shining a light at such a high angle of 70 degrees here. And this is not the right number because water and air, it's a much lower angle needed. I'm just exaggerating. But what will happen is, if the light ray gets bent so much that it bends like this, it bends so that it's on the surface interface now. Now this angle is 90 degrees. So as a result, the critical angle would be 70 degrees in this scenario or this diagram. Maybe this is like water with something in it, because water needs a much lower angle. Remember what was it? Remember we measured it on the board when I showed you that video? Anybody remember what the number was? A little higher. It was around 48.7 was the number. So the real angle, critical angle for water is around 48. I'm just picking random stuff. So make believe this is water with maybe some particles in it that are changing its index of refraction. So the idea though, again, is that the critical angle is really the incident angle. But it's a new name when the light gets bent along the surface. Now, what if I exceeded 70 degrees? You did this in the lab. When the angle got greater than the critical angle, instead of the refracted ray being along the surface, what ended up happening? What ended up happening?
It gets total internal reflection.
Becomes total internal reflection. So it gets refracted so much. So for example, if you increase this 70, and now you're angling it, at maybe the next angle is like 80 or something. Well, the light gets refracted so much that it goes beyond 90 degrees. And this angle now is like 110 or something like that. That's what total internal reflection really is. Again, that's what total internal reflection is. So if you wanted to see if you had total internal reflection, you could really just calculate theta r. And if theta r is bigger than 90, you have total internal reflection. Because that's physically what's happening here. This angle of refraction is more than 90, so it seems like it's reflection, although it's not. It seems like reflection. But it's still refracting the light. It's still bending the light. Let's see what else. I'm going to get to some math ones in a minute. I want to see if there's anything else I want to cover specifically. Let's talk about two more things before we get to math. How is n, the index of refraction, derived? Where does it come from? Why is its value always greater than 1? Why is it unitless? What are all these answers? Think back to where n really comes from.
Well, the reason it's not 1 is because if it was 1, then there like is no refraction, it would just go straight through as opposed to kind of going out in a separate way.
Okay, that's true physically, but mathematically with the equation that n is represented by. N equals something over something. What was it from your notes?
Meters per second over meters per second.
Yeah, so we had, remember it was like a speed over another speed, that was n was defined as? So what Alessia is alluding to is the unitless fact. This is meters per second over meters per second. So that's why n has no units. Why is n going to always be bigger than 1? Nora?
Because you can't travel faster than the speed of light.
So v, the denominator, is always going to be less than c. The numerator is always this. Right? We know this number. It's given on your formula sheet if you don't remember it. Well, the velocity is the velocity of light in whatever material it's in. So in anything except for a vacuum, this number is going to be smaller than this number. So as a result, you always get a number bigger than 1. Okay? Always greater than 1. So pick a number like 2.5 times 10 to the 8, whatever it is. Either way, this velocity is always less than whatever was at the top. Okay? So this index of refraction would be 1.5. 3 over 2. That's where the index of refraction comes from. Last thing before we get to the math problems. What about lenses? When you talk about lenses, first of all, what is a lens? What kind of lenses do we have? How are they used? Answer those questions for me. Marianne, give me something.
Well, there are two types of lenses, concave and convex, and mostly they kind of like bend the light to help usually it helps somebody see better in glasses.
Yeah, an application that we talked about, there's tons obviously, like telescopes, binoculars, they all have lenses in them. A camera has a lens in it. But the application we gave, as Marianne said, was using it as a corrective lens. So if you want, for example, somebody farsighted to be able to see, even though farsighted, again, farsighted means you can see far. If the person has trouble seeing close up, you give them reading glasses and they're bent a certain way so they can see close up. And then if they're nearsighted, the opposite, they can't see far, they wear glasses for distance. Let's talk about what's physically happening now. The first lens on the left is called what? On the left?
Convex.
Convex. The one on the right is concave. In the way you remember that, it kind of looks like a cave opening, okay? Now, convex lenses are converging lenses. It allows the light to do this. Okay, converge to a focal point, to some location. Your eyes are naturally converging lenses. Remember, your eyes take parallel light rays coming in, and they focus those rays on the retina in the back of your eye. Now, what about the other lens, this concave lens? What is it? Not converging, but?
Doesn't have a certain point, it's like everywhere.
Yeah, what's the opposite of converging?
Divergent.
Diverging. Diverging, diverging. Good. That's all right. Okay, so this is a concave lens, and it's diverging. Now, if you are farsighted, you can see far, and in your eye, what's physically happening is that the rays are focusing too far from the lens. So they need to converge earlier. So you use a converging lens for farsightedness. This is what farsightedness looks like. Here's your eye. Here's your eye's normal lens in the front. Here's the light rays coming into your eye. And the light rays focus back here. When really, where should they focus? On the retina, which is located at the very back of your eye. Your retina is right here on that dot. But when you're farsighted, the rays focus too far from the lens. So since you want them to converge a little bit sooner, you use a convex lens to cause them to converge a little bit earlier. And then what do you do about the other part?
They're focusing too soon, so they can't.
Exactly. Very good. These are focusing too soon. So here, we've got an example where the light comes in, right? And they focus maybe right here. When clearly, we want them to focus on the retina over here. So you use a diverging lens. You put a simple diverging lens in the front of the eye, and as a result, when you put this diverging lens in the front of the eye, it causes it to focus a little bit further away, or spread out the rays, so that they don't really converge until they hit the retina. Remember, when you put glasses on, you're diverging the rays, and then they're hitting your lens in your eye, which is then converging the rays, but originally they were converging too soon. So by diverging them, and then hitting your naturally occurring lens in your eye, and then converging them, you're kind of like taking them, spreading them apart, and then bringing them back together. Here, what's happening is, instead of them landing back here, you just want to bring them together sooner. Okay, you want them to converge sooner, so they hit this retina with a convergent lens. All right, let's do some math now. So, you should definitely know Snell's law, which is given, but you should know how to use it. Snell's law tells us this. Where I stands for incident and R stands for refracted. So if you're trying to find the refracted angle, you're solving for theta R. Your calculator needs to be in degree mode. Don't borrow someone's calculator tomorrow and forget to do it because they don't have it in degree mode. Use your own. If you're trying to find theta, you need to use the sine inverse to do that. So if you're trying to solve for theta R, you need to divide by NR, and then take the sine inverse of this entire left-hand side. Give me another 30 seconds. And that will solve for the refracted angle. Now, remember, if the refracted angle is either 90, or if the refracted angle is 90, it means that the incident angle that you had was the critical angle. If the refracted angle you get is more than 90, it means that you have total internal reflection occurring. Now, there's another formula, obviously, that we went over, that you should also be familiar with, and this is the critical angle formula. The critical angle equaled the sine inverse of over. Now, the refracted medium is usually going to be something like water. So this would be like a 1, and this might be glass. Or did I say water?
Yeah.
Air. The refracted medium will usually be something like air. And then the incident medium that it starts with is either like a diamond or water, where the light tries to escape but it can't. So what you need to remember is that the numerator is always less than the denominator when you're doing sine inverse. If you get an error, it's probably that these are switched. Okay? I didn't go into anything with chapter 17, section 1. It's on the test. Okay? It's what we did yesterday, though. So review your notes from yesterday, go over the ideas, go over the idea of charge, what charge means, the milk and oil drop experiment that told us that the fundamental charge is really an electron, and then the 3 types of ways to charge: by contact, by induction, and by polarization. There's 2 words for polarization. One has to do with light waves, one has to do with charging by polarization, which was the last thing we ended with yesterday. You need to use the context of the problem to understand what I'm asking about. If I say explain how a charge can be induced by polarization, I'm not talking about polarized light now. I'm talking about charges. If I ask you about light being polarized, I'm not talking about charges then. So use the context of the problem to help you.
You're gonna give us like a table.
I'll give you the table of all values you need. You don't have to memorize in numbers. Okay, so n values will be given, any table with numbers, any with numbers will be given on the test. Okay?